Okay, can you hear me? Yeah. Okay, yeah, thanks to the organizers for asking me to give a course about the moduli space of curves, and thanks everyone for being here. So let me just kind of, yeah, okay. So basically, it'll be a very, very easy elementary introduction to the moduli space of curves, and some intersection theory on it. Somehow the goal is not to be very precise, but at the end that you'll be able to compute some intersection numbers. So if you're able to compute some intersection numbers at the end of this thing, that's great. So basically, I'll kind of talk about the modular space of curves, MGN, its compactification, and then some sub-ring of the cohomology on MGN bar, which is where we will do all of our computations. Right, and then finally, a way to be able to compute some intersection numbers. Yeah, so I was in the middle of writing references. So more or less, I'll follow, an easier version of Zwankin's notes. So this is called the Introduction to the Modular Space of Curves and their Intersection Theory. If at some point you get like really annoyed with me that I'm not giving you enough details, I'm very sketchy, like just go and read Zwankin. That's a lot better. There's some course notes from a course at the University of Bonn given by Johannes Schmidt. It's called the modular space of curves. That's also a really nice introduction to the modular space. There's some notes that I wanted to mention of Renzo Cavalieri, and this is just in the genus 0 story. It's called the modular space of pointed rational curves. Yeah, and finally, I guess I wanted to say that there's some stuff that I will not. Okay, there's also like archive lectures by like Rahul Pandey. It's called the Calculus for the Modular Space of Curves. These are also some really fun notes if you want to take a look. Okay, so first of all, I mean, I'm not sure if this is a good way to start a talk at all in general, but let me just tell you that, but maybe this is something that needs to be said because I will not say very much about the relation to topological recursion, which is somehow what this conference is supposed to be. But I'll say that they're very closely related. So there's a lot of the structure of TR can be viewed as the structure of the modular space of curves somehow. Okay, and doing intersection theory on the modular space of curves is very closely related to the topological recursion formula. Okay, great. So yeah, but basically I will not say almost anything about that, except maybe at the very end, and we'll see if we get there. Depends on how much time I have. Okay, so let's start. I'll try to keep some numbering from my notes. Okay, let's start by talking about modular space of smooth curves. Right? I mean, apart from like the relation to TR, I mean, probably you shouldn't really have to need that much motivation to talk about the modular space of curves. I mean, if you're interested in geometry in any way, right? Like if you're interested in geometry, you want to study curves. Well, you want to look at all curves, right? You want to look at the modular space. Okay, so I'll use G for the genus of a curve. Always, it will be some non-negative integer, and n for the number of for n greater than or equal to 0. This will be the number of marked points. So what are the objects that we're interested in? We're interested in curves of genus G with n mark points. What does that look like? I will draw it sort of in the over C. I will always work over the complex numbers. And in the real picture, right, this is the Riemann surface. So it has all these holes. It has G holes. And mark points that I will try and denote by like X. Okay, so it has all these mark points. We'll call them P1, P2, all the way to Pn. This is going to be a genus G curve with n mark points. And we want to study all such curves. Right? So this is what the modular space is. So call it MGN. Oh, okay, maybe a couple of things. Curve is always going to be projective, or if you want, compact. Okay, so first we want to look at smooth curves. So this is going to be the modular space of smooth curves. Smooth complex curves of genus G. With n mark points. We require that the mark points are distinct. Okay, and we will always consider this up to isomorphism, right? Like usual. Okay, so this is a perfectly well-defined set, but we want more, right? We want to understand the geometry, so we want to give it more structure. We want to think of it either as algebraic variety or maybe as a manifold. Okay. Did I say everything? So the first main problem is that there is geometry, but it's not so simple. So MGN is not manifold or algebraic variety. And the reason is that curves have automorphisms. It's not very straightforward to explain why this is a problem for thinking about it as a manifold or variety, but in some sense, the issue is that if you want to think of moduli spaces, then you don't want to just think about the curves, but you want to sort of think about families of curves. And when you have automorphisms, you're able to construct families that are locally trivial, but globally not trivial. Right? You glue them like non-trivially using these automorphisms. And that's sort of the reason that's the reason that it's not a manifold or variety. So what do I mean that curves have automorphisms, right? Let's see. So example, right? Here's an example of a curve. It's a curve of genus 0. P1. Interrupt me whenever you have questions, and if something is unclear or if I write something wrong, also please let me know. And P1 has automorphisms. What is automorphism group of P1? It's PGL2, the set of 2 by 2 matrices right? Such that AD minus BC not 0, and you view these as projective. So you think of basically rescaling doesn't affect it, right? So A, B, C, D is the same. Okay. I'm probably boring a lot of you. I hope that you already know a lot about the modular space of curves, that you don't mind. Okay, how does it act? So I have P1, let's say I have coordinate Z. The action is just Z, then to AZ plus B. Okay. Okay, so the automorphism group is pretty big, first of all. It's infinite. There's a way to get rid of automorphisms, so to speak, right? And that's by just marking a few points on P1. So exercise is that if I would just mark 3 points on P1, let me call them T1, T2, and T3. There's a unique element, PGL2, that takes these points to specific points that you want. Okay, and here I will want them to be just, let's choose them to be 0, 1, and infinity. Okay, and this essentially uses up all of the automorphisms of the curve, right? So this is unique, the automorphisms. Okay, good. Another example, genus 1 curve. So it's a complex torus, elliptic curve, it's a complex torus. The elliptic curve also has automorphisms, right? Because, well, the elliptic curve is a group, right? And the automorphism of the elliptic curve at least contains the elliptic curve itself. It just acts by like addition. Okay. So that's also infinite. So okay. Theorem, fact.
Sorry, is there some subtlety in genus 1 or when 0 mark points, exactly 1 mark point?
Yeah, so I mean, I don't know, like if you, depends on how you define an elliptic curve, right? People usually define it with the choice of a point, yes, which is your origin, which is your 0 for the addition. Then of course not, because the 0 is going to get moved, right? When you act by the elliptic curve, it adds points, right? So your origin is just going to get moved.
So like N1, 0 and N1, 1 are very different.
They're very different, yes. They're very, very different. Yeah. So here, no mark points. Let me say. No mark. Okay. At least we're sort of lucky that the situations that I described sort of here are kind of the worst things that can happen, where the automorphism group is like really big, it's infinite. And the fact is that a curve with mark points, I guess I didn't really, maybe I didn't write down the notation, but it'll be like, I'll say P1 up to Pn, these are going to be the mark points on my curve C. The automorphism group is finite if and only if the Euler characteristic, which is it's negative. Okay, and this is just a way to say, well, there's actually only like finitely many things, many curves that are going to give us problems, and these are the following, right? So if I have Gn is 0, 0, that's there, right? And then we said, oh, we actually have to fix 3 things. So 0, 1, 0, 2 are bad, and this case here, just 1, 0. Okay, these are bad. Okay, so we basically, from now on, we just won't care about those ones. Okay. We'll just throw those out. I mean, things are still not as good as you would like, right? Ideally, you would just have no automorphisms, but you still have finite automorphisms. So, I mean, example, you have a hyperelliptic curve. Hyperelliptic curve. So, you know, something that's defined by some equation like this. D, let's say, minus I. This at least always has an automorphism, which is given by y goes to minus 1. Right? So there's at least some automorphism, which is a Z2 automorphism. Okay, so in general, we will have your moduli space will have points in the moduli curves will still have automorphisms even if you throw these. And we will have to deal with that. And a way to deal with that is to sort of just remember that curves actually have automorphisms. And this just leads to the following. And this pretty much like leads us to thinking about orbifolds. So orbifolds are going to be things. Okay, let me first write this down. So, but if
Sorry,
yeah.
what genus would be
No, it will have genus depending on the degree of this polynomial here. It can be it can be anything. Yeah, it just depends on the degree. Yeah. There's a map to a P1 that's degree 2.
P1?
Yeah, so I mean to a genus 0 curve. Right? I mean all elliptic curves have this form, right? And I assume that that's where the name comes from, but I'm not sure. Yeah. So I mean, in general, this is not going to give you like, if you're in genus 1, I mean, these are all of your curves. In general, this is not going to give you all of your curves, right? But there's some subset that's going to be this.
It's not zero.
Ah, okay. So it's not elliptic or rational, so it's hyperelliptic, I guess. It's like, yeah. Yeah. Okay, yeah. So if minus 2 plus n is greater than 0, so we have that condition there. This set that we wrote down there, MGN, is a smooth orbifold. Okay. I don't really want to get into like the definition of an orbifold, but it's enough. It's similar to the definition of a manifold. So there's some charts, and you glue these charts together. But these charts don't look like Cn anymore. They look like Cn, like quotient by a finite group. An orbifold is something that is covered by G, where G is finite. Okay. And really, the only thing that, I mean, you can more or less pretend that I'm going to just be talking about manifolds here. But just remember that if some of your curves are going to have automorphisms, right? And so and a point on an orbifold will have automorphisms. And this is pretty much the only thing that you will need to remember, at least for the purposes of what I will talk about. Okay, so yeah. Remember, pretend that you're in a manifold, but remember. Yes, thanks. Remember that points have automorphisms. Points of automorphisms have stabilizers. Good. Okay, so now let's look at some examples. Okay, so the first non-trivial one, right, is okay. So the complexity is sort of going to increase as you go up in genus and as you go up in the other characters, as you go down in the other characteristic. So first example, M03. So this is a genus 0 curve with 3 marked points. Right. But I already said, actually, you can use all the automorphisms of P1. You can use all of them, right, to take it to P1 with just 3 points that you choose, the 0, 1, and infinity. Okay, that's it. You're done. That's the only point that you have. This is the point. Okay. Okay, great. That's not such a bad moduli space. Pretty much, yeah. You've kind of used up all of your automorphisms, right, to move it to a point. So if I give you any genus 0 curve with 3 points, you can always use the automorphisms to put it to this one. It's going to be more complicated just because here. In general, your different curves will have different automorphisms. But yeah, at any point you can think of as just the curve modded out by its automorphism. Exactly. So that's the next thing that I would say. Thanks.
Can I think that all the time doing work with the holomorphic so that you always have Riemann surfaces and when it says morphism, you mean by holomorphisms, or I can think that throughout, or is it different?
Yes.
I want to think complex, right, and algebraic.
You can do whichever one you're comfortable with. It's totally fine. Yeah. Just remember that sometimes there's automorphisms, but otherwise, yes, you're fine. Right. So what a biholomorphic map between orbifolds is, it still requires. You still have to think about the fact that there is some quotient, right, by a finite group. But oh, here, yes, absolutely, yeah. Yes. Until we contact. We're not there yet. Okay. Yeah. So, second example. M04. Okay. What was that? That was P1 with 4 points. Okay. Now I'm going to use the same automorphism, right? I can bring the first 3 of my points to 0, 1, and infinity. And then the last point goes somewhere, right? So you at least see that it has 1 dimension, right? I only have 1 parameter left. This is sort of oh yeah, this is I think what Riemann called modulus, which is where the name moduli space comes from, right? It's the parameters that you're allowed to vary so that. Okay. Right. So yeah, we only have 1 thing, right? So you only have 1 dimension. But you also have to be careful, right? I said at the start that the mark points are not allowed to coincide. So t cannot be equal to 0, 1, or infinity. Okay, so what is this? This is actually a P1, which is all of my T, except I remove 3 points. Okay. Okay, great. So we can keep going. 105. Okay, I do the same trick. T3, T4, T5. I fix 3 of my points. Call it T and T prime now. Right, so now see I have T and T prime. T is not allowed to be 0, 1, or infinity. T prime is also not allowed to be 0, 1, or infinity. But also T and T prime are not allowed to be the same. So I have to remove the diagonal. Right? The diagonal is just the things where the points in P1 and both of the P1s are the same. Okay. So far we haven't really seen any of this, like I told you, you have to be careful, like finite groups and stuff, but I mean, this is all perfectly fine, right? So let's look at an example. You have to be careful about like finite stabilizers, but none of that happens here. Okay, let's look at an example where that actually happens. Maybe I just say that, like, well, nothing more interesting is going to happen in genus 0. This is pretty much all that's going to happen, just all the way down. So let's go to genus 1. In genus 1, remember that we have to fix 1 mark point. 1, 0 is not good. Okay. So what is this, right? This is the moduli of elliptic curves, but with a fixed point. Okay, well, an elliptic curve, right, you can also think of as just a complex torus, and you can just think about it as a complex structures on the torus. Okay, so let me say that this is to classify all such pointed elliptic curves with a marked point. It's enough to look at, well, complex tori. Right? What are complex tori? I mean, take a lattice. And you take the quotient. Okay. Up to like first of all, up to rescaling of the lattice. Okay, so I just use this rescaling to set one of my things to 1. This one, set 2 to 1. Okay, this is supposed to be 1. And then I only have 1 parameter. I'll call tau. Okay. Okay, so the problem is now just to classify lattices, right? And what is this? So this is tau is something in the upper half plane, first of all. But there's still symmetries, right? So tau, think of something in the upper half plane. But there's still symmetries. There's like change of basis of the lattice. And the change of basis is by the modular group. Okay, so say like in fact we actually need to classify lattices, and lattices are classified by the upper half plane up to the modular group. So SL2Z. SL2Z. How does SL2Z act, right? Now, so SL2Z, remember, it's just matrices. It's just matrices ABCD. Such that 80 minus BC is 1. And how does it act? It takes such a matrix, takes tau, A tau plus B, tau plus D. Okay, and So what you're looking for is basically like a fundamental domain of this SL2Z, right? And you might remember from like, I don't know, high school that the fundamental domain of SL2Z looks like this. Well, actually, I want SL2Z. Yeah. You're right, that the fundamental domain of PSL2Z is this thing, but I do want SL2Z here. So yeah, it's a good point, right? So I mean, basically, what happens, right? My matrices that are usually would quotient by the negative of the identity matrix, and the negative of the identity matrix does act by 1. And so, okay, so I'll get there in a second. I guess there's a reason that this one is put away. Right, so this point is like third root of unity. I mean, yeah. Okay, yeah. So right. So there's minus the. I mean, the orbifold structure I want is really actually for SL the quotient by SL2Z. What that means is that in this fundamental domain, right? If I would look at some point, some point here, it actually does have a Z2 stabilizer. And this is just the elliptic curve. I mean, elliptic curve is a hyperelliptic curve, right? And it always has a Z2 stabilizer. And this is the Z2 stabilizer that you see. Okay, so the orbifold structure that you want is in fact it's still this. Yeah, and there's some special points now, right? I mean, oh, sorry, I have to say, I mean, these are sort of glued together, right? This is the same as this one. Doing a good job with the colors. And this is actually glued. This is a unit circle. This point, right? You can check actually from there that it has a Z6 stabilizer, and this one has a Z4. Okay, so this is the orbifold structure. So the space is this thing, but I mean your points like sort of have stabilizers, and you have to remember that happens. Oh, okay. I should not have erased the previous examples because I wanted to make a point. And the point was that just recall, right? M04, we had, for example, P1 minus 3 points. Okay, this is not compact, right? So I'm missing these 3 points. Compact. You also see here, right, that there's this sort of pointed infinity that you're missing. It's also not compact. Oh. So just write it down, M11. It's actually just the upper half plane quotient by SL2Z. And it's not compact. Well, MGN in general is not compact. Let me draw some sort of like cartoon picture, right? Like why is this not compact here in M11? Well, generally I have an elliptic curve, right? It's nice and smooth, nice donut, and I have a marked point. And then I take one of these cycles here and I pinch it. Take sort of the limit so this is a nice thing in M11. and I pinch it, and I get something that looks like that. Right. They're touching. I mean, right? And this is not. Oh, sorry. The mark point is still there, and this is not an M. And this is the point that's at infinity. And if you'd really think about what happens here, I mean, you'll see that this is actually a nodal. This is the so-called nodal cubic. And so the point of this picture is that, well, in fact, if we want something compact, which we like, right? Compacts, like projective compact things, are really nice. You can do intersection theory on them, for example, without, yeah. And so we would like to have something compact. Okay, so that brings me to the compactification. And you know, like when you and you want something compact, but you still want a moduli space, and so it shouldn't be just that you're just throwing like points at random to like fill in the holes, right? But it should be that it's like still parameterizing some nice class of things. And the moral of this example is that you have to have nodal curves. So the idea is add nodal curves. Okay, nodes are Mild singularities. So add Mild singularities. And so let me define nodal curve. Yeah, a nodal curve is, so a curve, we will say that a curve C has a node at a point Q if locally around Q it looks like x times y equals 0 in C2, right? The set in C2. Okay, that's kind of what I tried to draw here. It's not too bad. It's not too singular. Okay, and we want to add nodal curves. Right, but adding like all nodal curves is somehow it's too naive, right? We still have to remember. Okay, well, why is that not going to work? First of all, right? So you know, if you have something compact, you would want, for example, if you take limits like this, right, where you're pinching cycles and so on, that the limit is still in the space. But if you just decide to add all nodes, right, so I could construct some family that looks like this, right? Let's take a curve with two genera, and then I sort of start adding nodes. Okay. So it's like a sequence. I had 3 nodes. So this one, remember, this was fine, right? This was perfectly. And I mean, I don't know. Like you can, it's sort of like heuristically, at least you see that if you take the limit of these things, right, you're not going to have something that's nice. I mean, it's just going to have infinite like components. So the problem is that we kind of forgot that we still need to have curves that have finite automorphisms. Okay. So we don't want to add all nodal curves, but we want to add curves that are called stable. Stable curve. A nodal curve. Okay, so I mean, yeah, I kind of said it in words, but if you take the limit, right? Yeah, I mean, this is, yeah, you get the idea. A nodal curve C is called stable. Oh, I should really write C with the mark points. If the automorphism group okay, this is actually exactly the same thing as saying that this is equivalent, saying that every connected component has to be has to have Euler characteristic negative. So the same thing as saying if you take, okay, let me say if you take the normalization, every component of the normalization, I'll say in a second how to think at least about what a normalization is, has Euler characteristic. Yeah, I'll just like forget about these p's for now, but they're always there. It's just easier to just write C tilde. Right, so let me say every component, we index it by V, so Euler characteristic negative. Okay, so what does that mean? I mean, I have a, so what does a stable curve look like? It looks like the following. And then maybe some genera, a bunch of more points. Okay, this one's stable. And what is a normalization? The one thing that you have to remember when making the normalization is just that the nodes, you should think of them still as more points. So basically, I just kind of separate them, right? I just detach all these things. But I still have to remember my nodes. So there were these nodes here. Okay. So now you see that this is stable because all of the components here are actually have Euler characteristic negative, right? This is the so you remember that you have to also count this blue dots as well. So this is a genus 0 thing with 3 points. This is genus 1 with many points, and this is genus 1 with more than enough points. So you're fine. So this curve is stable. And if I would just remove, so this is stable, right? But if I would remove, for example, one of these points, it would no longer be stable. Okay, I'll just say that. Right, if I would remove one of these points, then it would no longer be stable because you would get, when you take the normalization, you would get something with 2 mark points. Okay, and then, so, yeah, and this lets us define a compactification. No, please. Yeah, you can take also complex analytic neighborhoods. This is fine. Yeah. Yeah. Okay.
Okay. And then a nodal curve is a mark points will be nodal or
yeah. Okay. Thanks. So it's first of all, it should be really like at most nodal. It doesn't have to have nodes. If it does have nodes, the mark points are not allowed to be nodes. the mark points cannot be nodes. They are not allowed. They cannot be nodes. That's why I used Q before. That's right. Yeah, and I hope that I will do that all the time. So, if I don't, like, tell me. Yeah. So that's a good point. Maybe it's worth writing down. I mean, the mark points cannot be nodes. Mark points cannot be nodes. Here. Definition before theorem. Doesn't matter. Yeah. We define our modular space to be stable curves genus G, then mark points. This thing is a smooth or compact orbitals of dimension, complex dimension, 2g minus 3g plus. Okay. So that's basically the right class of curves to include in MGN, so that you get a compact modular space, right? And in here, obviously, like MGN inside MGN bar, there's obviously MGN, right? It's just the ones that don't have any nodes. Let me sort of try and like give you examples that maybe at least illustrates the fact that it's compact. I mean, proving this is, yeah. I guess it's hard. I haven't really looked at the proof. I mean, essentially, yeah. I won't say anything about the proof, but basically, like the idea is that you need to somehow make sure that all these like kind of limit things exist, and so you have to make sure that that you're able to do that. Like you're able to take limits of curves that degenerate and that are still inside this modular space. Okay, example. So how long am I supposed to talk actually? 50. Okay. No, it can be 0, right? Then if it's 0, then I just need, so the dimension here, it's fine, it's okay. So what are you worried about? I mean, if G would be 0, right, n would be at least 3. But n is 0, then G cannot be 0, right? It's not stable. Okay, sorry. Every time I write G and n, will always satisfy this. Okay, thanks. Yeah. So, yeah, anytime I write G and n, it will always satisfy this. We threw away like 0, 1, 0, 0, 0, 1, 0, 2, and 1, 0. We threw away. Like we don't care about those. Okay, so example. Well, M03 was already a point, right? It was compact. M04 bar. Okay, so what was M04? That was actually a P1, but we had to remove 3 points. We had to remove 3 points. Okay, and remember that these 3 points that we have removed came from, so if I was in here in this P1, right, I had I had, yeah, so I have these points, say 0, 1, infinity. And then P1 is sort of this last point that I was allowed to move around. Right? And we had to remove these points because t was not allowed to be 0, 1, or infinity. So what happens, right? Now if I take t to, let's say, 0, so the limit is t goes to 0. So when you try to collide these points, they basically refuse and they just leave. Okay. Maybe I shouldn't call them 1 infinity anymore. Let me just say some points. And then these two guys just leave. So you actually get a you get a curve that looks like this. Oh, and I said that I would use x for mark points. Okay. So this is one of those sort of limit points. Yeah, so I'm trying to yeah, nothing's pinching, right? Yeah, let me explain why this happens in a second, right? But let me just say that what you have to do is actually add the points where t goes to 0, t goes to 1, and t goes to infinity. And these are going to look like these kinds of points. I will explain in a second why this is true. But that means that I'm adding at the end 3 points to my M04 to get M04 bar. So this is just going to be a P1. I just put these 3 points back in. Okay, but why does that happen, right? We're not pinching anything. We're not getting a node. It's kind of hard to imagine. Oh, I want to write something. To see that, let's look at a family, right? Let's look at a family of curves. Looks like xy equals t. So, or xy equals tz squared, right, if you're projective. And now I want to take t goes to 0, right? In the real picture, oh, and I need to mark a bunch of points. So I need to mark points. Look at, I will mark the points 0, 1, 0. Right, so xy, is that squared, let's say? 1t1. And the sort of the real picture looks like this, right? Xy is t is some curve like this. And I've marked some points. But somehow, like, when I have a 0, right, they're sort of living at infinity. So let me just put those points like here at the end. Right, so these are 2 of my points. And then I have these points like 1t and t1. Here and here. And what happens when I take t goes to 0, right? I actually get xy equals 0. So I get these 2 lines. And what happens to these points, right? This point sort of went. And here, this point went here, this point went here, this point went here. This is the end, that's infinity. Right? And this is the real picture of this thing. Right? I have 2 points that live on one component, and I have 2 points that live on the other component. And there's a node. Okay. Yeah, so I hope that was kind of, yeah, okay, I'll repeat it. So okay, what do we want to know, right? So we want to know, okay, I'm saying if I take M04, I had this like one parameter t that I was sort of allowed to move around, but it was not allowed to hit 0, 1, or infinity. Now I'm saying when I hit, let's say 0, what happens is that the points that I didn't do anything to stay on this component, and it just the curve just sprouts a node, and the 2 points that kind of came together just leave. Why is that? So let me take a family of curves, right? So this is a family of curves, and I pick and I mark points, and I mark 4 points. So whenever t is not 0, right, these are 4 points on a curve. This is a real picture. That's there. Right. Now when t goes to 0, basically what happens is that the curve splits, right? I get 2 components. It's connected by a node, and 2 of the mark points go on one node, and 2 of the other ones go on the other node. Yeah.
How do you think about this now? Why did you think about this?
Yeah. Well, I mean, yeah. Well, I mean, how would you take a limit, right? So if you want to take a limit, basically, like algebraically, you have to write down a family of curves such that your limit point is going to be, in this case, we're trying to get like some stable curves, right? So you write down a family of stable curves such that your like limit point is also a stable curve, right?
How do you know what is the meaning of this? X, Y,
It's genus 0. I mean, it's just like from, I mean, it's a degree 2 curve. It's a degree 2 curve in P2, right? It's a degree 2 curve. And it's like I mean, when t goes to 0, right? That's exactly what I said as a node is, right? So I hope I. Yeah, to compute the genus of the curve. Yeah, there's some degree genus formula. Probably gonna get it wrong if I try to write it now, but this curve is degree 2 curves at genus. Yeah. Okay, I think I'm going like way slower than I thought. So I wanted to say, okay, so another thing. So we're kind of interested in the boundary. And you define the boundary in G bar is basically everything that was not in MGN bar. It's like the extra things that you had to add to make it compact. That's the boundary. And so here the boundary M04 is actually 4 curves. It's 3 points, right? And these 3 points correspond to like, okay, so now let me kind of mark them, right? It's like P1, P2, P3, P3, P4. Make these a bit smaller. It's P1, P3, P2, P4, and then there's the last one.
So sorry, this basic feature that the quantification in this case is given by the fact that as the buncher approaches, like they bubble up something and they leave something. What is this true like in the check? This is a way to
Yes.
in the check.
Yes. This is a good way to visualize it in general if you don't do anything to the other mark points, right? If you keep everything else fixed and you just bring 2 of them together, then they always bubble off into like into a component like this. With 2 points and the node. The 2 that came together kind of. Yeah. Yeah. Thanks. Yeah, it's a good way to think about it. Yeah. And so basically, I've kind of already told you all of the things that happen. So remember, well, all of the things that happen up to like all of the simple things that can happen, where you go to the boundary, which is, and the other one, where I remember, M11 bar. This has some orbifold structure, so I'm not going to be able to write something down that's easy like this, right? But it's really just the boundary here. It's just this nodal curve. It's this nodal cubic. Okay. And that's kind of the point at infinity in the fundamental domain that I was trying to do. Okay, so in general, the boundary of the Mozart space is really interesting. Let me try to get that. The cartoon picture, right, of MGN bar in general. The interior of this like square I'm going to think of as like MGN. So let's say, I mean, just do something 2, 1, right? So a point here is an MGN bar. And in the interior, it's going to look like, what is a point in the interior going to look like? It's going to look like that. Okay, so it's like perfectly nice and smooth curve with two genus 2 and 1 mark point. No, I want to do something more. Let's do 1, 2. Okay, and maybe if I go to like the boundary here, so if I go to like this boundary here, what does that look like, right? Maybe I pinch like one of these cycles, the only one that's here. Okay, and maybe this is supposed to be like, I can also go to the boundary in a different way, which is to bring these 2 mark points together. So let's say I go here, then I bring these 2 mark points together. Then what happens, right? We said that they just leave. Okay. Actually, there's this like sort of, these are sort of codimension 1. And if I go in like codimension 2, like both of these things can. So this point here is going to be like, okay, so I pinch a cycle and I bring them together. Looks like that. So I mean, this kind of illustrates, I hope, what the boundary generally looks like. So your codimension 1 things are, if you like the observation from this picture, right, is that like in codimension 1, what you're doing is that you're creating 1 node, right? Like 2 different ways, but you're creating a node. And when you go here now in codimension 2, you actually have 2 nodes. Okay, so this brings us like, I mean, this is something really very important about MGN bar, which is that the boundary MGN bar, we'll see some more interesting things like very soon, but let me just say that this picture is supposed to show that the boundary has a stratification by the number of nodes. I mean, this is just a way of saying what I just said, right? If I go to, like to codimension 1 things, then I'm going to have 1 node, and then if I go to like lower, then I get 2, and then if I go again, then I get like, as I go deeper into the boundary, I create more and more nodes. Okay, so that's okay. So to study the boundary, it's useful to somehow not think about my curves like this instead, but to think of them in terms of stable graphs. So let me say, what do I mean by that? Okay. some curve that looks like this, let's say. So to any stable curve, you can draw its dual graph. And the way that you do this is the following. So to every component, you draw a vertex of your graph. Okay. So I have 3, so I'm going to draw 1, 2, 3. And inside the vertex, I'm going to write down the genus of that component. So this one is genus 1. This one is genus 0. This one is genus 2. To every node, I will draw an edge that connects the vertices. And to every marked point, I will draw a leaf. So it's like a, oh, this is 2. Stable curve. It's called a stable graph. Right. Yeah. So I'm not sure if I need this, but let me just say that if I have P1, P2, P3, P4, then I will just write them as 1, 2, 3. Again, let me just write down what I did. So to every, so I said to every connected component, I will draw a vertex. If that connected component has genus G, I will just assign the vertex a genus. If I have an edge, if I have a node, I'll draw an edge. And if I have a mark point, sorry, we're writing so low, I will draw a leaf. Okay. So I'm not defining what a stable graph is, but it's anything that comes from a stable curve. Okay. If you do this. And you can read off the stability, right? Like the fact that it's stable from the graph, right? This too. Oh, which one? Ah, yeah, thanks. Thank you. Yeah. So the genus, right? So the genus actually here is 4, right? Because you have to kind of think about this one as well. It came from maybe like pinch cycles or something, right? So you make this curve smooth. You just like connect everything. You get an extra genus. So it's 2 plus 1 plus 1 in the middle. And in fact, the genus of the stable graph is also 4. And the way that you count it is that you have to count the kind of loops in the graph. So it's 1 plus 2 plus 1. That's 4. Yeah, thanks, Danny. What I was going and stability, right? So that's genus, and then stability. Yeah, thanks. So that's the genus. Oh, I will use this notation. So if I have a stable curve C, I will call it like the associated stable graph, gamma C. And gamma in general, I will use to denote a stable graph. Stability. Yeah. So how do I see the stability from here, right? It's before that, maybe I want to say one more thing. Like, I also want to define like half edges. Right, and like the set of like, and half edge is like a leaf, so it's kind of half an edge, right? And like literally half an edge. Like the set of half edges is like half of edges and leaves. Okay, and because I mean the reason that you want to think about it is like this is, remember that I said that, you know, if you take the normalization of the curve, you wanted to remember that where the nodes came from, right? So you're kind of remembering them as well as mark points. So that's sort of what these half edges are doing. Okay, and finally, if I have a stable graph, I think I will denote its vertices. E will refer to the edges. That's all I care about, but maybe H will refer to the half edges. Okay, and then stability, finally, is that for every vertex V, the graph is stable if 2GV minus GV is the genus of the vertex, minus 2 plus n is greater than 0, where n is the number of half edges associated to that vertex. Okay, so NV is the number of half edges. So here you count the leaves and the half edges that are attached to these things. Okay, so here it's like 3. Okay. Okay, some quick examples, right? What stable graphs look like? You can have, I don't know, genus 1 vertex, right? Half edges. You can have these kinds of loops, like edges connected to itself. And this, for example, would be genus 2. I think I don't know, some other example. You can have that. Genus 2, 1, 0. Okay. Yeah. Yes. Yeah. Yeah. So yeah. Yeah. Exactly. That if I have multiple edges connecting to the same vertex, or? Yeah, like here. Yeah, yeah, yeah. You can have two nodes in the, yeah, exactly. Yeah. Yeah. Oh, and I will call. Yeah, so I mean, this is G is 2, N is 1, right? This is, okay, I'm not going to count the genus there. But I will say that the graph gamma is of type stable graph gamma, a stable graph. Just notation, a stable graph gamma is of type Gn if the stable curve, I mean, if the graph has genus G with n leaves, graph has genus G with n leaves, or equivalently, it came from a stable curve of genus G and n markings. Okay. Yeah, I should really put numbers to these edges, but it's lazy. Okay, right. So finally, we'll get to the stratification. So if gamma is a stable graph of type, it's a stable graph. Let gamma be a stable graph of type Gn. And I define the following set. Is a set of curves whose dual graph is isomorphic to the stable graph that you chose. So it's all the curves whose dual graph will look like this graph. This is a set inside MGN bar. And here maybe is that MGN bar is just the disjoint union of all of these guys, right? Where gamma is of type Gn. And this is called the stratification of space.
Say more about how you identify the graphs.
Here? Yeah, so I mean it's... Oh, yeah, so here... think about that one. I mean, yes, the graphs do have automorphisms, right? But here I just mean...
And you taking graphs which are decorated by these numbers in the genes of the components.
Yeah, I mean... I'm not sure how to say it. Yeah, but I mean, yeah, but I guess the question is more like, oh, is like, you know, like there's some orbifold structure. So I don't know. Is that the question? Or wait, maybe I'm getting confused.
Yeah, well.
Yeah. Yeah, let me kind of gloss over that for the moment. So just think about it as a subset here. And I think I will say something useful soon. Yeah. That's right. That's right. Yeah. Yeah. It's like what you would. Yeah. It's the automorphism. The isomorph. Ah. So. Yeah.
Says about the structure, you should also quotient by.
Is that true? Because, yeah, I mean, if I would think about like the image of the gluing map, right? I think it's true that if I would think about it as the image of the gluing map, then you get like multiple copies because the automorphism of the graph. But define like this, I don't think I need to do that. Yeah. So, but that's what I said that I will in a second I will say something maybe kind of useful. Yeah. But yeah, an isomorphism of graphs is kind of what you would expect. It takes like vertices to vertices with the same genus, and yeah, the half edges to the half edges as well. The leaves to the leaves. Okay. Right. So, but let's do an example. Oh, M05. Okay, so what does this look like for M05 bar? So what are all the stable graphs that appear? So first of all, the dimension is said 3g minus 3 plus n. Right, that's 0 minus 3 plus 5, that's 2. So like the biggest stratum, right? So in codimension 0 is the smooth curve, right? And the dual graph of this curve is just is a genus 0 vertex with 5. Okay. Now I go down to codimension 1. What happens? You take, right? So I said the codimension is. So yeah, what do you do, right? You take two of your mark points to each other, and so 3 of them stay on 1, get connected by an edge, and you get 2. Okay. And now you can do the same thing again for this component here, right? It has 3. So go down again in codimension 2, right? And that's the end. I mean, my dimension is just 2. And that, so you take 2 of these to each other, and then they leave as well. That's it. Okay, so observations, right? The first thing.
Because the labels of
Well, I'm just no. I mean, this graph does. Mm-hmm.
This is because of the 3 possibilities of
That's right. That's right. Yes, that's right. That's right. Yeah. Yeah, that's right. Yeah, thanks. Yeah, so some observations, right? The first thing, yeah, so I mean, it's like I've not left them labeled, but really you should like label all of them and list all of them. Yeah, so the first observation is that the codimension is equal to the number of edges. Which is the number of nodes. And the second observation is actually that all of the strata are actually parameterized by the moduli spaces themselves, like lower dimensional moduli spaces. Right? So what do I mean? So this one, well, this we know, right? It's a smooth curve of genus 0 with 5 mark points, 0, 5, here. But this one is actually a smooth curve of genus G with 4 mark points, right? The normalization, and 1 with 3 mark points. So I can think of this as something in M04 and M03. Right? And what is this one? This one's like M03 here, M03, 03. Okay. Okay, and this is, yeah, and this is important. So this is so the point. The point is that lower dimensional strata are also, or strata are also oh, and the other thing is that if you would take the closures of these strata here, then you kind of get the ones that are below it as well. But they're just, but what are those? That's just like compactifications of these things. So if I take these strata here, I take the closures of them. These are just the product of NGN bars. Right? Where my V runs over all versus. This, yeah, I mean, if I would, yeah, so now if I would write down, okay, yeah, so now you see the, okay, maybe I'll just say this now, I wanted to say this later, but now you see there's a map from this to MGN bar. Right, what do? You take all of these guys. Remember that we were keeping track of where the half edges are on the edges, right? So you just glue them together. And we call, okay, so this, we'll talk about this a little bit more later. So this is the gluing map. It's called the gluing map. And you literally just glue the different ones together, right? So if I would have this and this, then I just glue it along this edge. Okay, and this map has degree equal to the automorphism of the graph. Yeah. How do you glue it together? Oh, so right. So for every MGN, so for every stable graph, right? So I have so the illustration maybe right is here, right? So I give you this one here, this piece here. That was something in M04, and this one is in M03. But I also remembered that actually the graph does remember that there's the data of like what half edge is attached to what vertex, and you just glue those things together. Yeah. Okay. No, actually, now I kind of. So now I should say maybe. Here? But it could have nodes. I would still be able to glue them together, right? So maybe I would take something like the M04 boundary is going to be like this thing, right? And then I would still be able to glue them together. Sorry, yeah. Okay, let me picture. Draw a picture. So what do you glue, right? So let's say I'm in M04. So let's think about this gluing map. The degree of the gluing map is the automorphism. Is the cardinality of the automorphism. Yes, thanks. So if you want to define, so when you identify the closures of the strata, right, there's some factor of this automorphism because it's the images this map. There's some automorphism. There's some degree this map is not. So I think. Okay, so yeah. What do I glue, right? So for example, I have. I kind of want to. I just wanted to illustrate the gluing map for this example here. I got sorry, maybe you're right.
Because the gluing will do only what the edges in your graph. The boundary to have edges.
Yeah. Yeah, but the thing is that I could still be in the closure, right? I could.
compactification of M05, then you have your combinatorial description by graph, just telling you what you can add. So then, if you will take each of these pieces and then you take a compactification of each of them, then you will add more than you want to add to your M05. I think that Eva is right that here you should not take a compactification. You're gluing only along the things which are connected by edges.
No, I mean I don't see the problem. Like, so I mean, for example, I could glue a curve that's like this, right? I could glue a curve that's this one. That, and that has like a point here, sort of something that came from a node here, right? And then I glue it with right, and I just glue it together. I don't see the problem.
Sorry, is it a product or maybe it is a union, like over processes? So I have a problem with the dimension. This is like a product. Yeah.
Oh, there's. It is a product. It is a product. Just that you have to think. You have to remember that the genus of the curve is not just the sum of the genera of the individual vertices, right? But you have to take into account the loops.
But okay,
yeah.
My problem was that if you do this, you can do this of course, and then you can also take another graph. You can encode the same kind of picture using a different graph, so then you don't have a decomposition of your space into strata.
No, but these are the closures of the strata that we're talking about, right? The strata themselves, like, yeah, I agree that the decomposition into strata is only you're not allowed to like degenerate this graph further.
Yeah.
Yeah. But the closures, right? Or the closures will also include everything that's like when you further degenerate your graphs. Right? Okay. So I agree that the formula, like so it's the closures of the strata that we're talking about that has this image, right? The strata themselves are not these. Okay. Okay. I think I'm like way too slow. Yeah. Yeah, exactly. Yeah, that's the one. Yeah, to clarify, when I write disjoint union, right, I have to actually take not the closures of the strata, but like just the ones that are the curves that are just isomorphic to the graph. Okay. All right. So yeah, okay. I think I'm going to skip that. Doesn't matter. It'll be an exercise. Okay. Let's get into some intersection theory. Right? So, now I want to talk about some intersection theory on empty. So first, maybe I want to explain a little bit of like intersection theory in general. Okay, and here I really will pretend that things are. So am I supposed to stop at 12:50 or?
Yeah, you can take 15 more minutes.
I'll just take like maybe 10 more minutes. And kind of... Okay. Yeah, sorry guys.
And since you're supposed to.
Sorry? Okay, so yeah, I want to talk about a little bit of intersection theory, and like here I'll really pretend that things are like either, if you want, smooth projective varieties or manifolds, compact manifolds, and I will tell you just things, a couple of things that you have to be careful about when you're working with orbifolds or stacks. So let's say X, Y, smooth, projective varieties, so compact. First thing that we'll be interested in is the cohomology. So this is cohomology. It has a natural ring structure with Q coefficients. This is something that we need to do because we're actually working with stacks. Oh, so it's a ring, right? It has a product called the cup product. Okay, what do? I take a class here, theta, cup product. So I can multiply things together. And I will want to like sort of integrate top dimensional cohomology classes. So it'll be like a mx to q. Okay, and if you're comfortable just thinking about it as like differential forms, it's like just integrating like top dimensional forms, right? Or you can think about it using like Poincare duality. It's just like something living in homology, and then just take the degree. This is what I'll call like integral over x. This is Poincare duality. And here, I should say that if this degree map, when you're on an orbifold, you have to be careful. You have to count points with automorphisms. Okay, so the degree of a point, an MGN bar, let's say, degree of like a curve, be like 1 over the automorphism. Okay, so when you count there, you have to be careful. You have to just take into account all these automorphisms. Okay, example, if you're not so familiar with like homology, is the cohomology of projective space. So
This is the reason why you say Q and not Z.
this is a reason why you say Q and not Z. Example. Vector space. Cohomology ring. Projective space is a class of H living in quotient by n. H is a degree 2. Okay, this is called the hyperplane class, and it's Poincare dual. It's Poincare dual to the class of a hyperplane. So hyperplane in Pn is something that's just defined by like a linear function. You get a Pn minus 1 at the end, and H is like Poincare dual with this class. So Pn minus 1. Oh,
Yes.
um, that's right. Yeah, thanks. So yeah, this is some linear something sitting here linearly, and the point array dual thing of this class is the hyperplane class in cohomology. And I need to also say something about Chern classes. Right, so if I have so if you're comfortable thinking about it algebra geometrically, then a line bundle on a variety, right, is just going to be given by some divisor. And the first Chern class of this line bundle, you'll just think of as like, what is a divisor, right? It's something like sum over AI, DI. Just think of as like in H2. Okay, another way to think about it is just really think about this as a line bundle and take some section, some zero section, some meromorphic section, and think about the divisor of the zeros and poles. I'll call this like Z. And if you can define one, the first Chern class of line bundle, be the Poincare dual, the class of the divisor. Next. That was the end of the example. And in some sense, if you had a trivial line bundle, then your first Chern class would be 0. And somehow the first Chern class of a line bundle just measures sort of how non-trivial the line bundle is. Very sketchy. So an example, right, in this like PN story. Example, right? On PN, you have a line bundle people call like O of 1, right? And these are in sections of O of 1 are like degree 1 section of O of 1 is a linear function. Okay, and so you would take the sort of the first Chern class of 1. That would actually section of 0 of 1 defines a linear function, right? That defines a Pn minus 1 inside Pn. And the first Chern class of 1 is just this, exactly this Pn minus 1, which we already said is this hyperplane class. This guy. Okay, and I'll say like one more thing, and then I'll stop, which is that we'll also need push forwards and pullbacks. So if F is a map x to y, you're able to like push forward homology classes x to y. If you think about cohomology as like given by like differential forms, this is like integrating along the fibers of this map. And if you just think about it as like the point, and on the Poincare dual side, it's just like the Poincare, it's just a dual class of just the image of x in here. So push forward this.
sometimes
Sorry, where? Yeah, I mean, yeah, okay. I see. I mean, the notation is, yeah, confusing, I guess. So, yeah. I mean, sorry, yeah, sorry, you shouldn't think about this as being like, it's not like d equals 1 here. It's the, yeah. Yeah, this is standard notation. It's not my notation. And what it means is that it's the line bundle on Pn whose sections are linear functions, so degree 1 things. That's what this 1 stands for. And so when you take a degree 1 in Pn, right, you cut out a Pn minus 1. Yeah. 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 I don't know if that helps, but I mean, well, it's just, yeah, I mean, you have to think about 1 as a divisor, right? And it's the divisor that corresponds to the hyperplane class. I'm not sure if that's true. Sorry, I have to think about that. But okay, maybe it's true. I have to think about that. But yeah. But I mean, you know, like when you write O of D, like D is a divisor. And when I write O of 1 here, I don't mean it as a divisor. I just mean like O of 1 is the thing that has sections that are linear functions. But maybe what you're saying is still true. I can't think when I'm standing here. Oh yeah, sorry. So the last thing, no, a couple things more. I have pullbacks. F upper star. It's a pullback. And a pullback is, you can think about it on the Poincare dual as just the inverse image of Y. It's the class, the cohomology class that's dual to the inverse image. So we have push forwards and pullbacks. Push forward. Pullback. And push forward and pullback satisfy a very nice formula, like together, known as the projection formula. That's the last thing I'll say today. I'm sorry. Okay, I take a class alpha, let's say on X. I pull it back along F. I cup it with another class beta that lives in Y. Oh, sorry, Y. So I pull it back to X. I cup it with another class here, and then I want to take the push forward of this whole thing. Okay. And when you do this, you get alpha up the push forward of beta. Okay. And this formula is known as the projection formula. Sorry, my F's are kind of. Okay, and we will use this to compute intersection numbers in the following way. So if I would, for example, if I would have an integral of, where should I integrate? Upper star, there's an X, yeah, so if upper star alpha, beta. Okay, the projection formula actually implies the following thing. It's actually the integral in Y. That's not very hard. I mean, the way that, I mean, one way to think about integration is like pushing forward to a point, and you just like kind of first push forward to y, and then you push forward to y. So, okay, I'll stop, and I'm really sorry for going over time.